Welcome to the 2011 lecture series on business and the environment. I'm Reed Lifset, the Associate Director of the Industrial Environmental Management Program and Chair of the lecture series here at the School of Forestry and Environmental Studies. Through this lecture series, started in 1991, we seek to bring corporate executives and others to the Yale School of Forestry and Environmental Studies to talk about topics of current interest and, in many cases, cutting-edge developments in environmental management, policy, and science. We value the additional perspective that business people bring to our discussions at the Yale Environment School and the opportunity to have students and faculty meet them and for them to meet us. In the past, we've explored such topics as the emerging role of life cycle-oriented management and product take-back, the environmental impact of the service industries, and green domestic markets in developing countries. The IEM program, the sponsor of the series, is a research and teaching unit within Yale's Environment School. Under its auspices is a track in the master's program in this lecture series and the editorship of the Journal of Industrial Ecology. Be sure to grab some brochures at the back. The lecture series is supported by a small endowment, the Joel Omura Kurihara Fund. Joel was a graduate of the Environment School and the School of Management in 1991. He went to work for Conrail and was active in the Global Environmental Management Initiative. He was very bright, very committed, and very energetic believer in the importance of greening corporate practice. When he died 18 years ago, Conrail, his colleagues, family, and friends established a memorial to honor him. His parents asked that the funds be used to support this series because they think it captures well his commitment to dialogue about business and the environment. This year, I'm pleased to announce that we have a very special lecture series with the support from Nestle Waters North America. The theme is Producers, Packaging, and Public Policy. The lecture series explores the topic of extended producer responsibility, also known as EPR, and packaging. EPR is a policy strategy that makes producers responsible for their products when they become waste. The goal of the lecture series this year is to explore the advantages and disadvantages of the application of EPR to packaging waste and municipal solid waste more generally in the U.S. Nestle Waters North America, the market leader in bottled water in North America and a division of Nestle SA, the global food and beverage company, is seeking to significantly improve the recycling of beverage containers and all recyclable packaging materials. As part of that effort, they're supporting discussion and debate over the feasibility and effectiveness of EPR in the U.S. And we have a representative here, Mike Washburn from Nestle Waters. Keep America Beautiful, a U.S. nonprofit organization promoting litter and waste reduction, and the Resource Recovery Forum, a UK-based international nonprofit network of organizations interested in sustainable waste management, are assisting in publicizing the lecture series on EPR. The first talk in our series is by Dr. Carol Lavender Law, a leading researcher on the topic of marine plastic debris. Dr. Law's talk on plastic marine debris is one of several in this year's series that will set the context for debates over public policy towards plastic packaging. Plastic debris in marine environments, often called garbage patches, is a growing concern that is raising questions about materials choice and waste management for packaging and other products. A research oceanographer with SEA, Dr. Law received her undergraduate training in mathematics from Duke University and a doctorate from the Scripps Institution of Oceanography in 2001. SEA is an educational institution dedicated to exploration, understanding, and stewardship of the oceans that specializes in taking college students to the deep ocean on a traditional sailing vessel to learn about the sea. As part of its SEA semester program, SEA has been collecting data on plastic marine debris for more than a quarter of a century, generating a unique and powerful data set. Analysis based on that data culminated this fall in the publication of a widely read article in the journal Science. Other speakers in the series this year will address the role of biodegradability in packaging waste management, the relationship between materials choice and packaging design on the one hand, and waste infrastructure on the other, and the findings from life cycle assessments of packaging, the history of EPR in North America, and the history of U.S. federal policy towards packaging waste. Many of the lectures in the series will take the form of webinars. If you would like to be notified of the various lectures by email, please be sure to sign up on the list just outside the lecture hall. The lecture by Dr. Law is being videotaped and will be available on the website of the Yale School of Forestry and Environmental Studies. Also, please note that a class will be held in this room immediately after the talk, so we need to clear the room promptly. Thus, it is with considerable pleasure and anticipation and gratitude for an incredible drive this morning that I turn the podium over to Dr. Law, who will tell us about the science behind ocean garbage patches. Thanks.
Okay, well, thank you very much, Reed, for inviting me to come speak to you today, and thank you all for braving icy sidewalks, roads, etc., to come here and talk about trash. What I hope you take from today's talk is an accurate picture of the problem of marine debris in the oceans, and that's one based on scientific study. Now, this picture may be at odds with what you've heard about the issue of garbage patches in the media. And first and foremost is the misleading nature of that term, which is why it is italicized and in quotes in the title of my talk. I should say right off the bat, that is not to say that ocean pollution, especially with respect to plastic, is not a real environmental concern. But at the end of the talk, you may find yourself wondering, what exactly do we know about this environmental problem? Because at this point, there really are far more questions that are remaining that have yet been answered. So most of the awareness of this environmental problem has been focused on what's been called, in particular, the Great Pacific Garbage Patch, or you may have heard more recently about the Great Atlantic Garbage Patch. And I'm sure you're familiar with this issue. How many people have heard of this phenomenon before? Yeah, most people in the room. I suspect what you have heard is that there is some sort of floating landfill in the ocean that is twice the size of Texas or France or the United States, that there is more plastic than plankton floating around in the ocean. And if you do a Google Images search, you'll find pictures like these floating around the web. Plastic, very thick piles of debris, so thick that you could walk on them. And some people are even proposing cleaning up this debris and building plastic island habitats in the middle of the ocean. So you should be very wary. These pictures, by the way, are also used by reputable people. You see that even Oprah Winfrey says this is the most shocking thing I've ever seen. But if you actually look a little bit closely, you'll notice that there are generally no captions associated with these images, and they are not attributed. So they're not telling you what you're actually looking at. That's not to say these are photoshopped in any way, but they may not be the pictures from the middle of the ocean. In fact, they're not. These images do perpetuate common misconceptions of the problem of plastic waste in the ocean. There is no floating landfill. There typically aren't even large masses of accumulated trash or even things that you can detect by eye. Most of the waste that is floating around the ocean is not even visible to an observer from the deck of the ship, let alone from aircraft or satellite. So today, and instead actually, so big X through those pictures. What you would see if you went into the places that have been dubbed these garbage patches are images that are more similar to this. This is from the Sargasso Sea, an area of the subtropical North Atlantic that I'll be spending a lot of time talking about today. And you see, generally speaking, very nice, can you guys see that? There, okay. Flat seas and sort of cloudy skies, just generally ocean. Now, occasionally from the deck of the ship, you might see some common everyday items float by, such as a boot or a plastic bucket. And this is, in fact, very shocking, especially if you've spent any amount of time far from land on a ship. This is not a common occurrence. You may also see some lost fishing gear or some items that you don't really know what it is, but you can tell that it's some sort of piece of floating debris. But in any case, those are very different images from the slide I just showed you. So what I'm going to do today is spend time talking about the science behind these issues using the most extensive data set ever collected in any ocean, compiled on plastic marine debris. So to give you a sense of where we're going today, we're going to spend a little bit of time talking about the background to this issue. Why does this pollution problem exist in the ocean? Specifically, what is marine debris? And I'm going to spend some time introducing the plastic debris data set collected by Sea Education Association over the past quarter century and building on that. And I put in parentheses Atlantic because we do also operate in the Pacific Ocean, although we've only been operating there for about the past 9 years. So we have data from from the Pacific region as well as the Atlantic, although I won't be talking about that today. And then I'm going to describe the geographical distribution of this floating plastic debris and use oceanographic data to explain this distribution from surface current patterns, explaining why it collects where it does. And then finally, I'll be describing trends in the floating plastic debris from our 22-year data set and discuss factors that might help explain the trends that we observe. And that's including sort of estimates of the source of plastic to the ocean as well as removal mechanisms away from the surface of the ocean. And then finally, we'll wrap up with some of the outstanding research questions. So let's begin with what is marine debris. By definition, marine debris is any solid man-made material that's processed or manufactured that persists in the marine environment. And the marine environment includes beaches, coastlines, marshes, and other wetlands, and also the immensely vast yet infrequently explored open ocean, which tends to suffer from the out-of-sight, out-of-mind mentality. Marine debris can consist of many different materials, aluminum, glass, paper, any kind of packaging that we use, any kind of waste that you would find out there. It's estimated, loosely estimated, that 60 to 80% of marine debris is composed of plastic. And if you look at some of these images, which are land-based images, you can see certainly that plastic is a large component. From volunteer beach cleanups and associated standardized surveys of debris conducted by the Ocean Conservancy over the past 25 years or so, we do have some pretty good numbers on the type of debris that collects on beaches. But there have been very few studies of marine debris in the open ocean itself. Although, in fact, the first observations of floating plastic in the ocean were made in the early 1970s in the Atlantic Ocean and in the late 1970s in the Pacific Ocean. So this is not a new phenomenon. The studies in the open ocean have focused on what is collected at the sea surface, and in fact, most of what is collected at the sea surface is composed of plastic. So why is plastic so pervasive? Well, as you know, plastic is a synthetic material. It's an organic polymer that is traditionally derived from petroleum. By design, the properties of plastic are those you're familiar with. It is lightweight, which means that most, but not all, plastic materials are buoyant in seawater. They float. Plastic is also designed to be strong, meaning it's very difficult to break apart mechanically. It is durable, and while it does experience some amount of photodegradation by exposure to UV radiation, that weakens the material, but it doesn't actually degrade it. So the plastic itself, the polymer, is highly resistant to biodegradation in the environment. And plastic is also relatively inexpensive to produce. And what this does is create a perception that the plastic is really a disposable material. So the result is that plastic is very persistent in the environment, whether it's marine or otherwise. In the ocean, the lifetime of plastic is not known. Exposure, as I said, to UV radiation and also the turbulent energy of the waves in the surface ocean environment do act to break down pieces of plastic into smaller fragments. But to the best of our knowledge and to the best of our observations thus far, that material does remain plastic down to perhaps the molecular level. The raw material of plastic products are shown here. These are plastic resin pellets or industrial resin pellets. And in this photograph, you see that these are really millimeters in size, typically spherical or cylindrical. They do come in a variety of colors. Many are sort of white or off-white, but you'll see other colors of these materials. And these are made of virgin plastic resins. So there are a number of different materials. If you look at your water bottle, for instance, you'll see on the bottom there's a code that has a little number inside. And in this case, this has a number 1. That means it's PET. That's the type of plastic material it's made of. So any of these consumer products start out as these resin pellets, which are then shipped to manufacturers of those consumer products and formed into the items that we use every day. So to set the scene, let's talk a little bit about the impacts of plastic in the marine environment. So there are a number of known environmental impacts, and I'm sure you'll be familiar with many of these, especially the issue of entanglement. You see pictures like this on the web, and they're very disturbing images. Entanglement is mostly an issue for very large, sort of discarded fishing gear in particular, very large items of debris that get wrapped around these particular types of animals like seals and sea lions and turtles. The type of debris I'm going to talk about today is generally not associated with entanglement. Ingestion. We know that plastic debris is ingested by everything from marine mammals and turtles down to seabirds and fish. And what I'm showing here are some images of a lace and albatross that were taken from Curry Atoll in the Northwest Hawaiian Islands. And you see here a mother albatross feeding its chick, and then nearby another albatross chick that has died, and the contents of the stomach of the fish, of the bird rather, are shown on this in this picture. And although you can't really see, is it possible to dim the lights in the front a little bit, maybe, to help with the images? Oh, I guess our person left. Thank you. In any case, what you can see here is there's actually a huge amount of plastic. In fact, the stomach contents of that bird weighed, thank you very much, weighed about 370 grams, and 270 grams of that were plastic. And you can even see items that you recognize like cigarette lighters here. So that brings about cartoons like this. And maybe you've also seen images from photographer Chris Jordan, who went to Midway Island and took just in situ photographs, just went and didn't disturb bird carcasses at all, but took photographs like this one where you can see, again, bottle caps and lighters. And I encourage you to visit that site. It's really startling. So we know ingestion is an issue, especially for larger organisms, but we also know that smaller organisms, even down to the planktonic level or invertebrates, will ingest plastic. Obviously, that is probably not good for them. Okay, organic pollutants. We know that particular types of plastic resins can act as sort of sponges in the marine environment and essentially attract and bind pollutants that are already present in the ocean water. Examples are DDT, PCBs, and PAHs. We also know that the plastics themselves can leach other additives into the marine environment that are also harmful chemicals, persistent organic pollutants that can be carcinogenic or mutagenic or endocrine disruptors. So we know that that also is a negative impact. And then finally, floating debris, here I show a piece of lost fishing gear that was pulled aboard on one of our ships, acts as a concentrator, basically creating micro ecosystems. So we have, when we pulled aboard this piece of line, we found barnacles and crabs and all sorts of organisms that just don't belong out in the middle of the open ocean. So not only do they sort of attach themselves to this and travel along on as maybe a sort of a floating raft, but this can act as a transport mechanism for potentially invasive species throughout the oceans. So also negative impact. Now these are some of the impacts that we do know occur. There are also some that are sort of big questions. Right now, there's this issue of what kind of microbes are growing on plastic debris. I'm showing here an image of a very small fragment of plastic that was collected on a cruise last summer. And looking under high power magnification, you can see that there are small phytoplankton, single-celled phytoplankton growing, microbes that have yet to be identified, and then all of these secretions are microbial secretions. So we know that the plastic not only is attracting larger organisms like barnacles and crabs, but also there are microbial biofilms growing on there that, again, we're not sure what the species of these organisms are. We don't know if they belong in that part of the ocean or not. Associated with the persistent organic pollutants that are accumulating on those plastic particles is the question of whether or not, if those are ingested, those contaminants can transfer to the tissues of the organism that has eaten the plastic, and then taking that a step further, whether those contaminants are then concentrated up the food web and potentially ending up in our food supply. And there are a lot of steps in that chain of whether or not this is a threat to human health. But it certainly is a possibility, and there are people starting to look at those questions. We do know that in at least one seabird study, some of those toxins were found in the tissue of the seabird. So it's certainly possible, but a huge open question at this point. And lastly, nobody, to my knowledge, has been even thinking about what the possible chemical impacts are. If this plastic does degrade or partially degrades, leaches whatever kinds of components into the marine system, we really have no idea what that's doing to the chemistry of the ocean. So there are certainly reasons to be concerned about this problem. So you might ask yourself, well, if plastics are so bad, why aren't they banned from the ocean? Well, they are, in fact, through an international regulation called MARPOL Annex 5, which was adopted in 1988. It is illegal to dump plastic of any kind into any part of the ocean. So there are strict guidelines for ships at sea about where they can dump different types of garbage. And in fact, just about anything else can be dumped into the ocean, but everywhere plastic is banned. So this is a good thing, and it's been in play for quite a while now, but there are some issues. As you might imagine, it's very difficult to enforce a global ocean-wide ban on plastic dumping. So unintentional dumping persists. I've lost plastic bit of something over the side of a ship, but I'm sure intentional dumping still occurs at sea. This also doesn't address inputs from land, and that reminds me, I forgot to talk about the source of plastic to the ocean. So let me just take a step back. How does the plastic actually get into the ocean? We know that it gets in from land sources and from sources at sea. So here I'm focusing on ships and at-sea platforms like oil platforms, for instance. We know that plastic is entering, again, either intentional dumping, even though it's been banned, or unintentional losses from those ships and platforms. Plastic is also entering from land, and it's coming from land in a number of ways, through waterways such as rivers or municipal outflows or sewage outflows. Basically, all rivers end up in the ocean. We also know that any kind of beach litter will be washed out to sea once the incoming tide comes in. Also, debris can be deposited on the beach in that way. And then finally, the wind can carry debris from land out to sea. And if you think about some of the images after Hurricane Katrina, we're talking large boats also, in addition to your plastic candy wrapper. So there are a number of different mechanisms. It's not known what proportion of waste comes from those sources, although you will hear a lot that 80% of the plastic input into the ocean is coming from land. I have not been able to actually substantiate that estimate. Okay, so back to where we were. So why this isn't necessarily helping, obviously this doesn't address those sources of plastic from land. And also, plastic in the ocean persists for decades to centuries or longer. We don't actually know the lifetime. So we still have plenty of plastic in the ocean, even though you can't throw it overboard from your fishing boat. So what do we know about plastic debris in the ocean? Well, at Sea Education Association, faculty and students have been studying the issue of plastic marine debris for more than 25 years now. And as Reed said, SEA is a nonprofit educational institution based in Woods Hole, Massachusetts on Cape Cod. And our primary program is the Sea Semester program, which is offered to undergraduates. So undergraduates come to our campus for 6 weeks and take coursework in marine science, maritime literature, history, and policy, and also practical seamanship. And then we take them out to sea on one of our 2 tall sailing ships that is outfitted for oceanographic research, either the Corwith Kramer, which sails in the Atlantic and Caribbean, or the Robert C. Siemens, which operates in the North and South Pacific. So students, when they are on board the ship for their 6-week research cruises, are actually full-fledged members of the ship's crew. They are handling the sails, steering the ship, working in the galley to prepare meals in the engine room, and they're working in the laboratory to collect oceanographic research for independent research projects that they have designed on shore. And they carry out that full research project from conception on shore to full completion on board the ship in a 12-week period. So this is really the cornerstone of what we do, is collect state-of-the-art ocean measurements that are comparable to what you would find from the major oceanographic institutions. And we collect that data for student use for their independent study projects. So what that means is that each voyage has a scientific mission that is really defined by the undergraduates and carried out on board those 6-week cruises. So to give you a sense of where we sail in the area I'm going to be talking about in terms of the Atlantic, this is an image showing you a typical year's worth of cruise tracks of the Corwith Kramer in the Atlantic Ocean and the Caribbean Sea. So North America, Central America, South America, here's the Caribbean Sea. The cruises are typically 6 weeks long, as I mentioned, and these cruise tracks are annually repeated. So every fall, the ship leaves from Woods Hole, sails south, and ends up in St. Croix, and then spends the winter in the Caribbean Sea and the southern Sargasso Sea, which is this portion of the North Atlantic Ocean here, doing research cruises. And then in the spring, we sail back up north to Woods Hole and spend the summer sailing around in the Gulf of Maine region. So that is really one of the critical factor is that we annually repeat these cruise tracks. So we've been able to build a time series of consistently collected oceanographic data over the past 25 years. In fact, 40 years is how long we've been doing the program, but given the evolution in oceanographic methods, we have certainly a robust 25-year data set. And it's really important to point out here that these data have been collected by more than 7,000 undergraduate students over that time period. And I think it really is unprecedented for undergraduates to be the ones primarily responsible for such an important baseline data set. So to give you a sense of how the plastic marine debris data are collected, I'm showing you this slide here. It is through a very sophisticated method of net towing. These are surface plankton net tows. Basically, this is a net that is 1 meter across and half a meter high, and it has a mesh of 335 microns. That's about 1/3 of a millimeter. So that is the mesh that's towed behind the mouth there. At the end, there is a little collection jar called the cod end jar. And we tow this net alongside the ship here, as you can see from the bird's eye view, for 1.8 kilometers. That's 1 nautical mile at a ship speed of 2 knots. So more or less, we tow this net alongside of the ship for approximately 30 minutes. If I can get a mouse, there we go. Just to give you a sense of what it's like being on the ship. Uh-oh. Did it start already? There we go. I do have a little movie here. Okay, so there is no sound. This is the ship sailing in the Sargasso Sea, and we're lowering this boom, which is what we attach the net to. To give you a sense of the size of the net, here you go. There are the people handling it. One of the benefits of this deployment is that it's very easy for students to learn how to do on their own very quickly. There's no winches involved, no heavy machinery. It's very difficult to get hurt. Here's the mouth view of the net as it's towing along the ocean surface there. And you see that the net is towed half in and half out of the ocean. So the idea is that we're really sampling less than the upper half meter of the ocean, truly measuring the sea surface. We bring the net back on board, we unscrew that cod end jar and dump the contents into a bucket. You'll see that they're pulling out something that looks like a piece of plastic sheeting. There's also some sargassum weed in the net. We dump that net contents into a bucket, and then the students do the real hard work here and spend time with the contents poured into a sieve, literally picking out pieces of plastic. And when we get into the heart of the area where it's collecting, this is a very tedious job. To give you a sense of what these samples look like, I'm showing you a couple of images here collected in the North Atlantic, and this is collected in the North Pacific to show you that really it's very similar samples in either ocean. This is that sieve that we just looked at in the previous picture and a pair of tweezers, and all these white bits that you see and blue colored pieces, this is all plastic. This is what the typical piece of plastic marine debris looks like. And on the right-hand side here, you see this is actually a Petri dish-sized sample. And in fact, in that, I think I forgot to write it down. In this sample, I think there's something like 250 pieces of plastic. And that is a lot of plastic compared to other parts of the ocean that I'll show you later really have 0. So to describe these pieces, they're really fragments from once larger items. They're irregularly shaped. They're often weathered, maybe with rounded edges, or perhaps faded from the sun. They are of various colors, and in general, we can't tell what type of object these fragments originated from. We can't tell whether it came from, a water bottle or a plastic bag. We also can't tell whether it came from New York City or France or some other part of the ocean. So we really don't know. Their histories remain a mystery. The exceptions to that are fragments of polypropylene line, which we know are most likely fishing line. And we also do see those plastic pellets that I mentioned in the beginning, those industrial-produced resin pellets. Those are easily distinguishable. So part of what we did was look at a subset of these samples to try to understand, in a broad sense, what the physical characteristics of this debris floating out in the ocean are. And the bottom line is it's small and it floats. So we looked at over 700 pieces of fragments collected in the Atlantic Ocean over a period of about 15 years, and we found that 88% of pieces are less than a centimeter in size, so that's smaller than your pinky fingernail. They also, more than 95% weighed less than 0.05 grams. That means it weighs less than a staple. So we're talking about very small bits of plastic. We also know that the plastic floats. And the way we did that was we actually measured the material density of those pieces. And so what's shown here is a histogram of density from samples collected in the open ocean and then samples collected on a beach near our campus on Cape Cod. So this is density increasing as you go to the right. What you see in the middle here, these bars are indicating the known manufacturers' density ranges of common plastic materials like polypropylene, the polyethylenes, polystyrene, PVC, and PET. So hopefully what you see is, this dashed line here is telling you what the typical density of surface seawater is for comparison. So if you look at the beach histogram, you'll notice that there certainly is a large proportion of low density material, but we really see material filling the entire range here of known plastic material densities. Whereas in the open ocean, we have very, very few samples that were denser than the density of surface seawater. And in fact, when we looked at those a little more closely, we realized most of them were chips of paint from the hull of the ship. So the net kind of bangs into the ship. That's a fairly common occurrence. So we know that the plastic we're collecting floats, which makes sense. That's why we're collecting it at the sea surface. But we can also determine that the materials from this, and also we did a further elemental analysis for carbon, nitrogen, and hydrogen. Again, we're able to compare to known values for these plastic resins, and we were able to say that yes, indeed, what we're collecting are the polyethylenes, HDPE and LDPE, and polypropylene. What we're not collecting includes PET, which is your common water bottle. So that's not to say that these materials, PET and PVC, and the solid polystyrene are not in the ocean. It means they are not floating at the surface of the ocean. So we don't have any measurements we don't really know where those materials end up or how much is in the ocean. Okay, so let's go to the question of where is this plastic in the ocean? How is it distributed in the North Atlantic? So what I'm showing you here is a map of the entire data set, which includes more than 6,100 surface net tows collected over that 22-year period. So to orient you, again, North America, South America, here's the Caribbean Sea in here. And each symbol represents the location of one plankton net tow, and it is shaded according to the concentration of plastic that we measured in the net. So what I should say is that the way that we compute concentration, students pick out individual pieces of plastic, and they're counted and carefully recorded, and then we divide that number by the width of ocean, basically the area of ocean that we've sampled. So the area of ocean is a 1 meter wide net towed for almost 2 kilometers. And to put that into everyday terms, we filter approximately 2,000 bathtubs worth of water in one net tow. So that's a lot of water, but again, when sort of looking at the vast expanse of the ocean, it's actually a very small piece of ocean. So when you divide by that area, you end up with plastic pieces per kilometer squared, and that's what these numbers are showing you here. So blues are zero plastic pieces are the dark blues, and then low number concentrations here. High concentrations are the warm colors, and then the black stars that you see here are the highest concentrations, more than 200,000 plastic pieces per kilometer squared. So first, let me say that in total, more than 64,000 pieces of plastic were pulled out of the nets over this time period. 62% of all of the tows that you see in this figure contained plastic. And another thing I should point out is that the way this figure was constructed was by plotting the low concentrations first. So there are many, many more tows than you can actually discern by eye here because the symbols are overlapping. So when we talk about these concentrations, you do have to keep in mind that these are numbers that are scaled up. We didn't collect 200,000 pieces of plastic. In those 2,000 bathtubs of water, the maximum number of pieces that we collected in any one tow, which I think was somewhere in here, was 1,069. And in general, of the tows that contained plastic, 50% of the tows had less than 20 pieces of plastic, and that's equivalent to 11,000 pieces per kilometer squared. So just to kind of give you a sense of what this figure is representing. So the question is this a lot of plastic or isn't it? That's one basic question. Our estimate, and this is a very broad brush estimate, lots of caveats to it, but our first guess estimate at the amount of plastic this represents floating in the ocean is 1,100 tons. So if you're starting with an image of a floating landfill, that's probably not a lot of plastic, but if you consider the fact that plastic never started in the ocean, I still think it's a fairly disturbing number. And this is obviously a lower bound as well. We're only sampling 6 cruise tracks a year. We're only sampling the surface, sea surface. We're only sampling things that are bigger than 1/3 of a millimeter in size. We have no idea what the vertical distribution is in the water column, et cetera. So certainly this is a minimum estimate. Okay, so let's take a look at the highest distribution of values. So if you notice, the red and the black symbols are all concentrated sort of in this region, which I'll call the subtropics. And I think one of the first surprising results is that if you look along the coastline, you really don't see the highest values there. And that's surprising because we do assume that land is one of the big sources of plastic to the ocean. So you might expect to see high values here decreasing offshore, but in fact we see the opposite situation. If you look at the average plastic concentration as a function of latitude, and it's tipped on its side here so we can compare with the map. So this is just 1 degree averages with a standard error associated with it. That's what the thin black bar is. You see that it really is fairly bell-shaped. You see fairly low concentrations of plastic at the higher latitudes, and then a huge increase here in the subtropics, and then a decrease down when you get into the tropics. And in fact, 83% of pieces that we collected were collected between 22 degrees north and 38 degrees north latitude. And that's roughly the latitude of somewhere in Cuba up to maybe close to Washington, D.C. So throughout the rest of the talk, oh, actually, let me back up. What we can't say from this, we can say now pretty robustly what the latitudinal limits are to this collection of plastic in the ocean. What we can't say is how far east this high concentration area extends. Now from this data set. So from here on out, I'm going to be referring to either the accumulation zone or the high concentration region. And when I talk about that, what I'm talking about really is this area here bounded by these latitude ranges. So why is the highest plastic content found here? To talk about this, we need to venture into a little bit of oceanography, which is good because that's actually what I know about most. This is a figure of a cartoon of the major surface currents of the ocean. And I'm just going to spend a couple minutes talking about it in case you're not familiar with our global ocean currents. First of all, you will see a very common feature in most of the ocean basins, and that is a sort of circulation that crosses the entire basin and is sort of a circular pattern. And you see that in all of the subtropical basins here, in the North Atlantic, in the North Pacific, although it kind of spans the image here, in the South Atlantic, in the South Pacific over here, in the Indian Ocean. And then you also, although it's harder to tell in this projection, there are also these same features, these closed circulation features up in the high latitude oceans in the North Atlantic and in the North Pacific, although interestingly not in the southern hemisphere, and that is because this current actually goes around the globe. That's the only current that entirely travels around the globe unimpeded. So these features, these closed circulation features, are termed gyres. And so we have two flavors of gyres. We have subtropical gyres and we have subpolar gyres. And what we're going to focus on are the subtropics. So let's take a look at actual real measurements of ocean currents rather than a cartoon image. What I'm showing here is one of the best estimates we have of the average surface circulation of the ocean, the average currents from state-of-the-art ocean measurements, and this is a 10-year average. So here we have a global map. Here are the Americas. So we have the Pacific Ocean, the Atlantic Ocean, the Indian Ocean. The way this figure is constructed is it's showing you these black squiggly lines that are very hard to make out are showing you the mean direction of flow, and the arrowheads are actually telling you what direction the flow is. These are called streamlines. The colors are showing you the average speed of the currents at any given place, with red being the fastest currents. Let's zoom in a little bit into the North Atlantic, since that's what we care about for the purposes of this talk. So in the North Atlantic, you can now see make out these arrowheads a little bit better. You can make out this same clockwise circulation, this subtropical gyre pattern, and you'll see a common feature, this very fast current going up along the east coast of the US. That's the Gulf Stream. I should point out, it's interesting, the fastest currents, average currents you see here are the Gulf Stream, the Florida current, and the loop current down here. Those average speeds are less than a meter per second. So in general, we're not talking about extremely fast speeds. But if you look now in the subtropical gyre region, you'll notice that these black streamlines are actually coming together and sort of dead ending in this area right here at about 30 degrees north. And this area is termed the subtropical convergence zone. That's because these currents are converging, they're coming together. And you notice in this zone, they're extremely slow, sluggish currents. So we're talking about speeds of less than 2 centimeters per second. So really, this is sort of where the currents are converging. It's very hard for water or anything drifting with the water to escape this region. Again, it's sort of a dead-end zone. Now, interestingly enough, you might imagine this would be a very nice place for plastic to collect because the currents are going to act to bring it together. And in fact, the relationship between the current patterns and the data set is very striking. So what I'm showing here is now our plastic concentration data mapped in a slightly different way with an overlay of a contour indicating the 2 centimeter per second speed from that previous image. So aside from the fact that it looks like a dog or other animal running away, what this is showing you is this is encompassing the extremely slow, sluggish area where those currents are converging. The plastic concentration map now is a spatially averaged map. It's been binned into half-degree latitude, longitude bins and smoothed with a filter to give us sort of a more average picture. And again, the color scheme, blue is low plastic and red is high plastic. And what you notice is this running dog really just about encompasses the area where we find the highest plastic concentration. So again, it's very simple, makes sense. The currents are coming together, the plastic is floating passively at the ocean surface, and so it is being brought into this accumulation zone. So we can actually pretty nicely say that we understand why the plastic is accumulating here. This is important it's important to note that this does not tell us the origin of the debris, and it doesn't tell us how long it has been there. And there have been some modeling studies, which I don't have time to talk about today, that can give us some first guesses. For instance, we think that debris could make its way to the center of this region from the East Coast in about a couple months. So we're talking actually very fast transit times because of that Gulf Stream carrying it quickly along the East Coast and then sort of ending up dumping into this area. So that's not to say all the debris comes from the East Coast, but any kind of floating plastic you put offshore here will end up here pretty quickly. So again, this doesn't tell us how far east this accumulation zone extends, but if you look at the previous picture, these sluggish currents actually do extend pretty much across the basin. So last summer we did go out on an expedition specifically to ask the question, how far does the highest concentration of plastic extend across the Atlantic? And this was the Plastics at Sea North Atlantic expedition. What I'm showing you here is a map of the subtropical North Atlantic. The blue dots show you the data set up until last summer, so the 6,100 net tows. And this shows you the cruise track that was followed last summer, extending east from Bermuda along 30 degrees north, along the center of that convergence zone, and then zigzagging back to try to survey that entire region, pretty much the western half of the North Atlantic. This is the MidAtlantic Ridge right here, which sort of marks the center of the North Atlantic basin. And what we found was pretty much uniformly high plastic. It doesn't ever decrease. In other words, we didn't find the edge of the accumulation zone. So here, kind of a similar figure, different color scheme, but plastic concentration where the highest values are purple and then this green, and pretty much uniformly more than 10,000 pieces per kilometer squared, whereas in the rest of the basin, just quickly going back to this picture, I forgot to mention the Caribbean, by the way, relatively low plastic concentration. Similarly, up here, even where there's high population centers, relatively low plastic concentrations. So, in this picture, there's really almost no blue. We're finding very high plastic concentrations extending the length of the cruise track. And in fact, we had the record breaker, more than 23,000 pieces of plastic in a single net tow. So those people were picking plastic for 2 days. And in fact, at some point, cut it off and just had to estimate how much was in the net. So there's no indication that that is decreasing. Unfortunately, it didn't answer our question. So we need to go out there again and keep going across the basin. If you're interested in learning about the expedition, we did have a website that discussed daily science results. There are photos and videos from sea. It was an outreach tool, so if you're interested, I encourage you to visit that website. Okay, so what do we know about other oceans, just briefly? What I'm going to show you is a video of some numerical model results. This is a numerical model that basically was constructed to have artificial plastic pieces seeded uniformly across the world ocean. And then the ocean was turned on and the surface currents were allowed to carry it where they may. And that evolution was observed for 10 years. And so the idea was to try to understand where globally these accumulation zones might be. So here we have this image, and I just think it's a pretty powerful image. You notice it started out all blue, so that was the uniformly high concentration. And over time, you see that this artificial debris moves away from the equator. That's because the currents are diverging there, carrying material away. Sorry, this repeats. So you see this divergence zone growing where there's no debris. And then you can see in these subtropical gyre regions, the North Atlantic like we've talked about, but also the North Pacific in the so-called North Pacific garbage patch. There are also these accumulation zones in the other subtropical gyres in the southern basins and also in the Indian Ocean. So right now there are some expeditions that are going out for the first time to try to measure these areas to see if there is in fact floating plastic debris there. And so far all indications are yes. But we don't know, again, this model is assuming a uniformly high concentration at the start. Obviously the sources of plastic to the ocean are varied. I mean, we can't assume that this was the initial condition for our real ocean. So while the mechanisms exist, we really have no idea how much debris we will find in any of these places. Okay, I'm going to shift gears a little bit and start talk quickly about the trends in plastic concentration that we have observed over the time period of our data set. So what I'm showing you here is annually averaged plastic concentration in that accumulation zone, so in that 22 to 38 degree north latitude range, as a function of time over the course of our data set, the 22-year time period. And the black lines, again, are the standard error associated with that. And first thing you notice is, well, gee, there's a lot of up and down. There's just a lot of variability. And in fact, that has been a little bit of a beast. We have worked long and hard to try to get a decent picture from that because it is highly variable. And if you look even on the, net toe to net toe, that stations that are about 30 or 50 miles apart, you can get a huge whopping amount of plastic in one and very little in the next. So there's just a lot of spatial variability, and this is telling us there's also a lot of temporal variability in the record. And in fact, if you fit a trend line, it's flat with an R-squared of 0. So we are observing no trend in plastic accumulation in the Atlantic Ocean. And this was surprising to us given the drastic increase in global production of plastic over this time period. So the question really is, all right, why do we not see a trend? So we have to think about the sources of plastic to the ocean. We also have to think about how plastic is being removed from the surface of the ocean. And again, to remind you, we're talking about plastic larger than 1/3 of a millimeter in size floating at the sea surface. This is not a picture of entirely what is in the ocean, but in that particular data set. So what is acting to potentially remove plastic from the surface of the ocean? So first, let's talk about the source. We thought, well, we need some kind of number about how much plastic might be entering the ocean. And because the sources are so dispersed, widespread, and not well quantified, we couldn't estimate it directly. So instead, we had to look at a proxy record, which is provided by the Environmental Protection Agency. They have reports of municipal solid waste in the United States back since 1960. So what I'm showing here is a time series of plastic waste generation, how much waste is generated, and then how much waste is discarded. And the difference between these is the amount that was actually recycled. So recycling is being taken into account into this curve. So plastic waste discards were greatly increasing over this time period. So given this, we feel like it is a reasonable assumption to say that the amount of plastic entering the ocean over that time period increased. It is important to note also this curve doesn't take into account dumping from ships. It also doesn't take into account anything about those resin pellets. Nonetheless, we are assuming it's increasing. So we have to investigate other aspects of the trend. First, could there be a sampling bias or variability in surface ocean currents? These are process questions. Does our figure actually represent what we think it does? And we think it does, so I'm not going to go into those details. We had thought about the source a little more carefully and thought, well, maybe even though more plastic is being entered into the waste stream, maybe it's not the kind that floats. And actually, the EPA does break this down by material. And so we looked at the curve of buoyant resins, the floating plastics, and in fact, those increased by about 25% over the time period. So again, we're pretty convinced that the amount of plastic that floats entering the ocean has increased. So then we had to look at removal mechanisms. What might be taking it away? We know that plastic pieces probably get to be smaller than 1/3 of a millimeter, and we're not measuring them, but we don't know how small they get or how much is out there. Sedimentation, we know that there can be those biofilms grow on the plastics, other encrusting organisms grow on the plastic, could make them dense enough that they have to sink away from the ocean. They sink away from the ocean surface again to where we can't measure them. No estimate, no good quantification of that. Shore deposition, we know that plastic is washing up on shore as well as being removed from shore. And we do have records from East Coast beaches which show that it's highly variable, seasonally dependent, depends on the beach. So this doesn't answer our question. And then finally, we know that organisms at various parts of the trophic level are eating plastic, but we don't know who eats it. We don't know what happens after it's eaten. We don't know what happens after the organism dies. So really, these are things that can remove it, but we have no idea how big any of those terms are. Very briefly, we did find one really important trend in our data set, and that's in those resin pellets. So we did distinguish those when picking them out. The students count pellets versus pieces. And over the entire region, we did see a statistically significant decrease in pellet concentration over time. And we believe this is in direct response to plastic industry's response to an EPA study, implementing measures to reduce the spillage of pellet transport and handling, the spillage in the transport and handling processes. So we think that this actually is a really nice demonstration of changing habits on shore that are then being observed in the ocean and could probably be a model study. Okay, wrapping up quickly because we're getting to the end here and there's a class. Outstanding questions, pretty much all of them are still outstanding. How much plastic is in the ocean? Where is it located? We can say generally we know where to look for it now, but again, because of the spatial variability, we haven't looked vertically in the water column. This is still very much an open question, although the question is a bit more refined. What is the fate of plastic marine debris? I just listed a number of mechanisms that may be taking it away from the surface, but we don't know what happens to it there or in other parts of the ocean. And what are the biological and chemical implications? We still just don't know. So in summary, SEA's plastic marine debris data set is the longest and most extensive record of plastic marine debris in any ocean, and I think these data provide a really important baseline. Again, undergraduates mostly responsible for this. Hope I've convinced you that plastic debris does accumulate in the subtropical convergence zone of the western North Atlantic and likely in other ocean basins, although please don't call it a garbage patch. And then despite a likely increase in source input, we do not observe a trend in the amount of debris in the North Atlantic, and we don't know why yet. We don't know where it's going. This is the case of the missing debris. And then finally, just to wrap it up, our garbage patch is a problem. You might think, let's just clean it up. What's the big deal? I think, after looking at what these pieces look like, it's just not feasible, and we can talk about why. You might also think, well, maybe these new biopolymers will prevent the problem from getting worse. And just a very strong word of warning about when you see the labeled biodegradable on any kind of product, you don't know what that means. Some of these products are, in fact, biodegradable, but only in very specific environmental facilities. We have no idea what happens to the marine environment. So in my opinion, the real solution is controlling the source of debris. And that means all of you perhaps reducing the amount of packaging that you consume, and also from the manufacturer's side of things, but also then reusing and recycling what you do use. And I guess I'll leave it there just with acknowledgments of my co-authors and also the work of the students that really did the bulk of the work. And if anybody's interested, there are reprints of the article outside and also information about SEA, and I'm also happy to chat with you afterwards. Thanks very much.